All right, family. So we're going to talk about volume using the disk method. And I suggest that you understand the basics of volume by parallel cross sections before you start this. Because if you understand kind of the principle of why parallel cross sections works, then this is just kind of like a consequence of that in a lot of ways. Okay, so the disk method applies to solids of revolution. And what is a solid of revolution? So this is the solid generated by rotating or revolving a planar region about the axis. Okay, so what do I mean by that? All right, so let's say that I have this curve here, and then let's say that I specifically decide that I'm going to take from here to here. So usually you have to define like what that region is. Okay, so this is like a little slice of the graph, and this is currently in 2D. So what I'm going to do is, now that I know what slice I'm talking about, I'm going to rotate this slice all the way around. And you want to think of, when I say rotate all the way around, think of it also as like coming out of the screen at you. So it goes from being a 2D object to a 3D object. So then what's that going to look like? Well, when I rotate, so if I just rotate all the way around, it's going to create this like cup shape kind of all the way around, or this cone shape really. And so that's what a solid of a revolution is. All right, so for this type of solid, the cross sections are disks. And if we go back to this, right, so depending on how I do my cross section, so in this case, if I were to slice this direction, right, so maybe I'll make it more clear. If I were to slice this direction, you can definitely see that these are disks, right? And so this also brings up another point. You can have cross sections going this direction, or they can go this direction, and we will talk about both in this video. All right, so anyways, so the cross sections are disks. So that really just looks like a circle, right? So the area of a disk, which like I said is the cross section, that would normally be pi r squared. Now, the thing is that this isn't always going to be like a perfect circle. You might have kind of wackier looking shapes. And so we're actually going to just slightly tweak this formula. Instead of it just being this pi r squared where I have to figure out, oh, what's r? The radius of the circle, depending on where we are in the cross section, might change. So instead we want to have a little bit more of a dynamic function. So we're going to have r of x. So this is going to be what our function is. So just to make sure that that makes sense. So coming back here, so if you think about it like with this shape here, right, the radius at this cross section is going to be different from the radius at this cross section. So the reason why we don't just have like a static formula, pi r squared, is because, like I said, the radius changes depending on where we're at. So this formula will allow us to compute those different radiuses depending on where we're at. Okay, so I have two formulas just to show you now. So we have the formula for finding volume by disks for rotation about the x-axis. Okay, so this is if we go around the x-axis. This should look very familiar if you understand the idea of volume by cross sections. This is literally the same formula, right? So I take just my volume of cross sections formula, and now when I come to what is that area formula, well, it is just that area for the disks like we just talked about. So it's the same formula as what we talked about in the last video. So you can find the volume now if you go around the x-axis, or like in the picture that I showed you, you can also go around the y-axis. So slightly different. So just notice now I've changed everything in terms of y. And if you are familiar with like area between curves, you would have done this before. So you can just kind of flip the way that you're kind of thinking about things. All right, so what do you say we jump into this then? So let's do a few examples. So first, let's say find the volume generated by revolving the bounded region around the x-axis. Okay, so a couple of things you got to do here. First, you've got to draw the situation. Now, I think that you can probably actually figure out what this looks like without me doing it for you. And I always say math is not a spectator sport. So I strongly recommend that you pause the video and you try to figure out, so remember, we're revolving this around the x-axis. So just visualize what this would look like and then hit play when you think you've figured it out. Okay, so I have So let's see, here's 1, 1. So let's see, I've got a curve that goes like this, right? So here's my x cubed. Okay, so I'm told that this is bounded by y equals 0, so I'll just go ahead and highlight that here. And then also x equals 1. So the region that we're talking about is this right here. And so remember, I'm revolving this around the x-axis, so it's going this way. So this is still kind of looking like a cone. It's just like a cone that looks curved, right? So if I were to draw this going all the way around, it would be a solid that looks like this, right? And again, you don't have to have this like perfect picture, but this just kind of helps you wrap your head around now the cross sections, because now I'm taking my cross sections like this, right? That's technically what we're doing here. Okay, so now let's set up our integral. All right, so my limits of integration, so I start at x equals 0 to x equals 1. And then it's going to be pi r squared. Let's see, maybe I'll just write that out. So pi r, maybe I'll say pi, sorry, r of x squared dx, which in this case, so now what is standing in the place of this radius function? Well, the radius is really going to be dependent, right, on where we are in this particular part of the curve, so this x cubed. So what I'll do then is I'll write x cubed, square it, dx. And now we have everything that we need to finish this, so let's make some space. Okay, so now it's just a matter of figuring out, you know, your algebra and all that good stuff. So this will just come out to x to the 6 pi. Actually, let's bring the pi out. Let's do it like that. Let's do pi, and then we'll just do x to the 6 dx. So you multiply the exponents together. So this will be pi times 1 over 7 x to the 7th, and then I evaluate this from 0 to 1, and so this just comes out to be pi over 7, right? So that's it. So there's the general idea. Okay, so next we're going to talk about finding the volume generated by revolving the bounded region around the y-axis. So just notice now we're talking about the y-axis here. So notice my function now is in terms of y. So I've got x equals the square root of 4 sine y. Y is going to be between 0 and pi, and x equals 0. All right. So I know that this is always the part that makes people kind of nervous. Like, this might be a function that you don't know totally what this looks like. And the only thing I really have to say about that is you've got to power through it. You cannot do this if you don't know what the region looks like. So I know it always feels very unpleasant, and now we've got this function in terms of y. But if you've made it to this point, you can hobble your way through this. So don't let the kind of negative self-talk of oh, I don't even know what this looks like. Oh, okay, I don't know what it looks like either. It's no big deal. We can get through this. So my suggestion, so we know that y is between 0 and pi. So why not start there? So let's draw a little axis here. Here's 0. Here's pi. So let's start there. So if I plug in 0 in for y, what do I get for x? Well, this will just become 4 times 0. Square root of 0 is 0. Okay, cool. And then if I plug in pi for y, so sine of pi is also 0. So at pi, I get x equals 0. So, I mean, you don't have to be a computer about this, right? You can do something as simple as just choosing a few points. So I've got 0, I've got pi. Why don't we choose pi over 2 to see if we can get the general shape of this thing? So if I plug pi over 2 into this, this becomes 4 times sine of pi over 2, which is just 4 times 1. Square root of 4 is 2. Okay. And so there's my shape. Now, if you're still nervous that this isn't quite right, you can always just find a few more points, right? You could go through and do it like that to make yourself more confident. So I'm going to just get rid of these for now so I have a nice smooth curve. I just want to have a smooth curve. Oops. Smooth curve. Okay. So after you draw the curve, then just look at your other bounds or other curves. So I need my y between 0 and pi, so we check that off. And then x equals 0. So x equals 0 is right here. So what are we talking about? We are talking about this region. This is the region that we're going to revolve around, okay? So if I revolve this way, it's going to be like a weird oblong shaped kind of sphere thing, right, in 3D. Okay, so then just remember, we've rotated this around the y-axis, so now we want to have an integral in terms of y. My limits of integration, so I'm going to look at the y-axis for this now since I'm doing everything in terms of y. So I start at 0 and I go to pi, so those are going to be my limits of integration. And then I'm going to have pi and then r squared. So my radius in this case is being generated by this curve here. So that's going to be square root of 4 sine y squared dy. And so once again, now I have everything that I need to get the integral set up, so we can make some space. Okay, and so from here, let's see, I'll bring the pi out. This will become 4 sine y dy. I guess I can also bring the 4 out. And so then to integrate sine of y, so the antiderivative there will be negative cosine y. So I'll just evaluate that from 0 to pi. So then, let's see, just plug it all in. All right, so this will be negative 1 minus negative 1. So now you just have to be, hardest part of this now, right, is all the negatives. So this will just come out to be 8 pi, because this will just end up being 2 plus 2. 2 times 4 pi is 8 pi. So there's the answer. Okay, so for our last one, so let's find the volume generated by revolving the bounded region about the line y equals 1. Okay, so revolving around another line can kind of disorient you a little bit. So I'm going to make another video kind of comparing revolving around a line versus revolving around an axis. So you can watch an example video on that, but let's just run with it for this one. So I think it's really helpful to have a little sketch in this case to get the party started. So, okay, so I'm going to have, it doesn't have to be perfect, right? So it's just, I've got this square root of 2x function. So I'll say that this is my square root of 2x. And then I have the line y equals 1, and then the line x equals 2. Now, the thing that might be really good to know is, first of all, just like, where does square root of 2x intersect with y equals 1? So if I just take a second to look at the math here, so I square both sides, and so then I get 2x equals 1, so I get x equals 1/2. Okay, so this is good to know because we also kind of need to know, like, so when I have x equals 2, where is that going to intersect? So this point right here, right, so this is where 2x and 1 intersect. So this right here is the point 1/2. So then if I plug in x equals 2, so what y coordinate do I get? So if I plug that in, I get 2 times 2, so obviously that's the square root of 4, so I get 2. So I have this other point, so I have, okay, so here will be my x equals 2. Again, it doesn't have to be a perfect drawing, right? It's just kind of there to like illustrate. So now if I draw all of this, so here's my line x equals 2. So this is kind of important to note because we are looking for the region bounded by these 3. So at first when you look at this, you might think it's this little corner in here, but the reality is now that I've drawn this out, it's this corner in here. So just something to kind of keep in mind because these kinds of things can kind of mess with you. So you just want to double check all your information. Okay, so now we can go ahead and think about our revolution. So I am revolving around the line y equals 1. So if I just draw like a little sketch, so there's my y-axis. So here's my line y equals 1. So I have some shape that looks like this, right? So this is the line that I'm revolving around. So I'm going around this way. So when I revolve around y equals 1, I get this like kind of cup looking shape. Okay, so that's what my situation is. And so then of course I'm taking, so for the radius of this, right? So remember my radius, so here's now where the here's the centering point, right? So the way that I want to think about this now is how do I describe from here to here? And in this case, I'm thinking top minus bottom. So the bottom in this case is not this axis, right? It's this line y equals 1. So this top part here, so actually let me clear out a little space just so I can finish writing this out. Okay, so this top part here is, so we have pi, of course, and then so I've got square root of 2x. There's my top part, but then the bottom part that gets to the bottom part of where this radius ends is this line here, y equals 1. So this is going to be square root of 2x minus 1 squared. Okay, and then of course we need to know our limits of integration, and so that's why having plotted these is really helpful. Sorry if you can hear my dog barking, by the way. You know, it's hazards of the job. Okay, so so we start here at 1/2 and we go to 2. Boom, there's my integral now, okay? So the thing is, you really have to kind of know what picture are you working with. Like, it doesn't have to be perfect, but a general idea. And then you have to really understand your revolution, because then you can go this like top minus bottom thing, okay? But I will have another video to kind of help orient you on this if you are feeling a little lost, okay? So let's keep going now. So I'm gonna now just integrate. All right, so let's go. So I'm going to bring the pi out, and I can go ahead now and FOIL all this other stuff. So this will be 4x minus 2 times the square root of 2x. Oh, sorry, did I say this should be 2x, not 4x, my bad. 2x minus 2 times the square root of 2x plus 1. Okay, so there's everything all FOILed out. So then this is going to become x squared minus, let's see, so I've got 2 square root of 2, and then, so just to be clear about this, so the way that you can think about this right here, I think of this as 2 square root of 2 x to the 1/2. So the square root of 2 can be broken out separately. Okay, so anyways, so then to integrate this, so this will be x to the 3/2, and then I'll multiply the whole thing by 2/3. And then all of this plus x. So now I just need to evaluate for these limits of integration. So let's see, so this will be pi, so I'll have 4 minus 4 square root of 2 over 3 times 2 to the 3/2 plus 2, and then all of that minus 1/2 squared minus, let's see, 4 square root of 2 over 3 times 1/2 to the 3/2 plus 1/2. So let's see. Okay, need a little more space. Okay, so from here now we just have to think a little. So I'm gonna have pi. So 4. So for this part here, so okay, we have to think about this for a moment. This is 2 to the 1/2, and this is 2 to the 3/2. So this actually becomes 2 to the 4/2. So this is really 2 squared. So maybe I'll write that off on the side just so you can see what I'm saying. So square root of 2 times 2 to the 3/2, that's 2 to the 1/2 times 2 to the 3/2, so that's 2 to the 4/2, so that's actually 2 squared. So what I'm saying is that this becomes minus 4 times 4 over 3, and then plus 2. And then for this other part, so let's see, this is 1/4 And then let's see. So if we do the same thing here now, so if I'll get rid of, I'll make some space. Okay, so I have 4 times 2 over 3. So 1 to the 3 halves doesn't matter. All I care about is this 1 over 2 to the 3 halves. And so this 4 times 2 to the 1 half. Okay, so I've got 4 times 2 to the 1 half over here. So what ends up happening is that this 1 half can cancel out with one of these. So this just becomes 2 over 2. So that's just going to be 4 over 3 times now just 1 over 2, because 2 over 2 simplifies to just 1. So then these will cancel out. So then I'm just left with 2 over 3, so minus 2/3. And then all of that plus 1 half. So I'll clear some space. And so then I have 6 minus, so 4 times 4 over 3, so it's going to be 16 over 3. And then this whole part will become 1 over 12. And so then finally I get to the final answer of 7 pi over 12. Okay, so I'm going to post just some other examples because I know it can get a little disorienting, and I'll try to also talk about things like graphs that maybe are hard to understand. So I'll post some hints on that to help you guys out. So check out the other example videos, but I'm going to end it here. And otherwise, I'm going to talk to you guys later. If you guys want to hit the like button or the subscribe button, that would be super cool. And I'll talk to you guys next time. Bye!